Hello everyone, I'm Keke Lian from Fudan University. It's my great honor to present our work here. This paper is the joint work of the researchers from Fudan University, the Pennsylvania State University, and the Tsinghua University. In Android system, many system services play a critical role in running important tasks, especially storing user and system data. For example, the account manager service help applications save user account information to avoid repeated login. However, the data storing process is rarely understood. In this work, we conduct the first systematic security study on the data storing process in Android system services. First of all, is the inconsistent lifecycle. Android applications send data to server process using bandar-based IPC. However, the data's lifecycle is inconsistent between applications and the system services. There is a time window between the data storing and the data releasing. Specifically, applications can freeze the data and recycle the occupied memory resources immediately, but the server process will hold the data for a long time in case that it will be used in the future. In this way, applications can make the server process consume more resources than themselves. Even worse, the Android system developers may also be confused about the life cycle of the data stored in system server. One example is the comments in Android source code. The developers wonder if they should actively recycle the data once the coder is died. Secondly, is the limited memory usage. Android enforces a set of limitations on each process's memory resources, including the system server process. For example, 512 megabytes for dedicated memory in Android 11. The exhaustion of these limited memory resources will raise the attention of Android recovery mechanisms, which are designed to reboot the system if it runs into an error state. As a result, with the capability of exhausting system server memory resources, attackers can control when the system will run into an error state. Lastly, is the lack of memory size check. A straightforward way to avoid memory resource exhaustion is checking the size of available memory before storing client data, but we found that some memory size checks are incomplete. Furthermore, the design flaws in Android IPC also pose challenges to enforce memory size checks. As shown in the figure, the left function does not check if the server's available memory is enough for the coming data. However, enforcing such checks needs to know the exact size of the required memory. That is, the server needs to know the array's length and the size of each string object. Unfortunately, the size of each string object is undefined and can be any int value. After understanding the data storing process, we found a new kind of space DOS attack. This attack relies on continuously injecting data into Android system services, which looks like continuously adding straws on the back of a camel. Therefore, we refer to this DOS attack as the straw attack. To detect such vulnerabilities automatically, we need to address several challenges. First, no detailed documentation can tell us how the data storing mechanisms are designed and implemented. Thus, we should cover as many as data storing instructions as possible. Second, there are a large number of system service interfaces in Android system with different functionalities. We need to support the testing of different interfaces with different inputs. Last, the memory changes of data storage operations are often subtle and hard to monitor. The operation may be tested thousands of times. Hence, we should monitor attack effects in a lightweight but efficient way. In this work, we propose StrawFuzzer, a directed gray box fuzzing-based approach, which combines static and dynamic analysis to detect and verify straw vulnerabilities in all Android system services. The basic idea is that we can continuously send input data to server process and monitor its memory size change to see if it can release the injected data timely. The main contributions of our work are summarized as these three aspects. First, our work is the first to systematically uncover the straw attacks in Android system, as well as revealing the root causes of this kind of vulnerability. And we design and implement a novel tool called the StrawFuzzer, which can automatically locate and exploit the vulnerable interfaces in Android services. We evaluate StrawFuzzer on 3 Android systems. The results show StrawFuzzer successfully exports 474 vulnerable interfaces in these systems and achieve various DOS consequences. Besides, we confirm popular Android applications can also suffer from straw attacks. Here is the overview architecture of StrawFuzzer, and it has 5 main phases as shown in this figure. The first phase is static analysis, aimed to locate vulnerability candidates and generate initial seeds for fuzzing them. Specifically, we identify containers from static fields and fields of singleton classes, which are thought to have a long life cycle, and we label operations that increase the size of selected containers as targeted data storing instructions. Then we perform backward control flow analysis and data flow analysis to locate the service interfaces that can inject data to these containers. For the selected interfaces, we generate initial states for them by extracting all branch conditions checked in the code, including constants and the return values of the method calls. Next, we test the interfaces and collect feedback information to evaluate each seed's quality in a lightweight way. In this phase, we focused on the seed's contribution in both exploration and exploitation. For exploration, we evaluate the seed based on the distance of the execution trace to the target data storing instruction. Specifically, we calculate the probability of reaching fuzzing targets for each triggered method. We assign each edge in the call graph with their reachability probability under the guidance of CFG, and use the probability as the distance. For exploitation, we focused on 2 types of memory resources, which are heap memory size and the size of some container objects with customized checks, as shown in the figure. The key problem here is that each input data has little influence on the memory size, even smaller than the regular change of server memory. Thus, we execute each seed multiple times to accumulate its influence so that we can observe the memory size change. After evaluating the seeds, we need to select the high-quality seeds for the next mutation. In general, StrawFuzzer favors seeds that get closer to the target in exploration phase or consume more memory in exploitation phase. But a critical obstacle here is how to balance the trade-off between exploration phase and the exploitation phase. Seeds with higher contribution do not always exploit the target in practice, due to some hard-to-satisfy path constraints or hard-to-exploit targets. Traditional fixed-time approaches rely on the empirical knowledge of the tested program and are impractical for the numerous Android service interfaces. Besides, the exploitation in StrawFuzzer can be time-consuming, and it's hard to determine the exact time needed. Thus, to balance the trade-off, StrawFuzzer uses an adaptive strategy to dynamically schedule them. Specifically, StrawFuzzer evaluates the seeds based on both its contribution and the selection times. For the selected seeds, we use different mutation strategies for exploration phase and exploitation phase. For the exploration phase, the goal is to reach the fuzzing targets, so we focus on the control flow related inputs of the tested interfaces in this stage. For the exploitation phase, the goal is to execute the targets and consume memory resources, so we only mutate the consumption-related inputs. Note that repeatedly invoking a service interface with the same inputs may not result in cumulative consequences due to the implicit redundancy checks, and we mutate the inputs towards a trend of enlarging memory size. Finally, for the exploit generation, as the exploits of straw vulnerabilities are affected by the runtime environment and the device performance, we collect high-quality seeds during fuzzing and inherit the mutation strategy used for exploitation stage. We evaluate StrawFuzzer on 3 Android systems with the latest security updates. As a result, straw father discovers 35 Unicode straw vulnerabilities and outputs 673 exploits in total, which affect 474 service interfaces. To evaluate the effectiveness of our adaptive strategy, we compare it with fixed-time strategy deployed by classical fathers like AIValGo. Especially, we randomly select 30 exploitable interfaces from our results and separately run straw father with adaptive strategy and 2 fixed-time strategies. The result shows that our adaptive strategy finds vulnerable interfaces faster than the fixed-time strategy and successfully identifies all 30 vulnerable interfaces, while fixed-time strategy fails to discover 2 of them before exceeding the timeout. This is because adaptive strategy leaves more time for exploitation. Now, we will show our main findings in the paper. This figure visualizes the numbers of affected interfaces per system service in Android 11. It shows that among the 200 system services, 35% of them contain exploitable interfaces. Moreover, the most affected interfaces are from a small set of services. We then analyze the permission requirements of the exploitable interfaces. We found that 158 of them require system permissions. This is because the vulnerabilities lie in the deserialization process, which are executed before the permission checks. We further analyze the location of vulnerable data storing instructions, as shown in the table. Though 54% of the vulnerabilities exist in the particular APIs, they only affect a small part of the exploitable interfaces. That is, over 90% of interfaces are exploitable because of the flaws in their deserialization process. To review when these vulnerabilities appear in Android, we further conduct a cross-version analysis from Android 8 to 11. It shows that about 6% of the interfaces are not exploitable when they are added into Android system, which indicates that these vulnerabilities are introduced by functional updates. To understand how straw vulnerabilities affect customized versions of Android, we additionally collect 3 Android devices from Huawei, Samsung, and Vivo. As these vendors forbid users to root their devices, we cannot rerun straw father on their systems. So we run the exploits generated by straw father on these devices directly. As a result, almost all vulnerabilities can be exploited successfully. We further analyze the straw vulnerabilities about the time it takes to render the device unusable. As a result, 90% of straw vulnerabilities can be successfully attacked within 78 seconds on average. This time can be further reduced by leveraging parallel execution. Like system services, the regular services in Android applications also need to store the application's own data. We collect 100 top free applications from Google Play and find that 76 of them suffer from straw vulnerabilities. Here is a vulnerability case that could lead to a permanent DOS attack. Account Manager Service provides an interface named Add Account explicitly that allows applications to store user accounts to a database in the external storage of the device. However, the interface does not limit the number of accounts that each application can add. Worse still, during the startup of Android system, the system server will automatically load all the accounts stored in this database, which exceeds the memory limitation, and the system crashes again. Finally, the Android system will fall into an endless loop. It continuously reboots and crashes, which is a permanent DOS attack to the device. In this paper, we conduct the first systematic study on the straw vulnerabilities, which can cause temporary or permanent DOS attacks. Then we propose straw father against the problems and discover 474 vulnerable interfaces, affecting 35% of real-world Android system services. Our findings show that more complete checks for data from applications are strongly needed. For more detailed information, welcome to read our paper. Thank you.
Keke, are you online?
Oh, yeah, I can hear you.
Okay, great. I know even though we are already 2:16, maybe we can still take a few questions. Questions from the audience? Maybe I can ask you a quick question. I think in your third contribution, you talk about these apps also vulnerable to these store vulnerabilities, and your paper mostly focused on the system service. And what's the difference between these apps and the system service, and why apps also vulnerable to this vulnerability?
Oh, well, thank you for the question. And the applications are also affected by this kind of vulnerability. On the one hand, applications inherit the vulnerabilities in Android deserialization process because they also use.
Today I want to talk about our.
What?
It's okay.
Hello?
Go ahead.
Okay. On the other hand, they implement vulnerable containers to store client's data, but without any limitation and protection. And in this work, we only focused on we mainly focus on the system, and we focus on the similarities between applications and systems. As for the differences, we leave that for the later study.
Great. So any other questions? All right.
Okay. So this is Zhibo from Purdue, and I wanna follow the Professor Lin's questions. Like, for I know the impact of the vulnerability in certain servers, but as you also mentioned that many user app contain the store vulnerabilities. So what's the real world impact of the store vulnerabilities in user app? I cannot think about a concrete case which will do some bad things. So could you give some insight about this?
Oh, well, that's a good question. As I said in the presentation, this kind of vulnerability can be leveraged by attackers to inject a large amount of data to the target process. For the application, we can just inject the data to the application's process through their exported components. And when they are running, and we can let the applications crash.
Okay, so then we can restart the app. Then all the things gone.
Yeah. For more serious results, the application may not be able to run normally again. They must be install the applications and reinstall the applications.
I see. Thanks for your answer.
All right, there's no more questions. Let's thank all the speakers in this session.